Hi, this is Sarah from University of Michigan, and I would like to introduce our work Efficient Computation Sharing for Multitask Visual Scene Understanding. Many computer vision applications, such as autonomous driving, require to produce multiple tasks for a single image to have a comprehensive understanding of that scene. For example, in self-driving system, the car needs to know what objects are around the car and how far they are from the car. As a result, designing a multitask module is critical for these kind of applications. Also, in most real-world scenarios, we need to perform the multitask module on a video input system. Therefore, our final goal is to generate an efficient module that can perform multiple tasks on a video input. One way to design a multitask module is designing separate models for each task. For this kind of system, we have to train each task separately, which can potentially lead to better performance. However, we also need to store and execute each model separately, which causes a significant memory allocations and extensive computation operations. Another way is to use multitask learning techniques, which learn a unified model to perform multiple tasks simultaneously. MTL system can reduce the memory and computation operations. However, they can lead to potentially suboptimal performance for some of the tasks due to task competition. So our proposed multitask module uses the strengths from both multiple single tasks and MTL. We propose to design multiple single tasks separately, as you can see here, but we want to somehow share the information and knowledge between the tasks to decrease the memory and computation. Additionally, for video inputs, we know that consecutive frames, they look really similar to each other in most video inputs. As a result, similar to the task domain, we want to somehow share the knowledge across time as well to reduce the computation across temporal domain. Here is our proposed scheme. We first split the task into one base task and multiple subtasks. Then for time t, we share the knowledge between the base task and subtask. Similarly, for time t plus 1, we borrow the information from time t to execute the model in time t plus 1. By sharing the knowledge across the task and time, we can reduce the memory and computation across both domains. First, to reduce the memory across the task domain, for each subtask, we use the weight of the base task plus a sparse delta weight matrix as shown here in this figure. In this way, for each subtask, we have to only store this sparse delta weight matrix, which can potentially lead to memory reduction. This step is called parameter sharing. Second, to reduce the computation for each subtask, we first introduce a sparse delta weight task activation matrix as a difference of activation between subtask and the base task. Then we reform the matrix multiplication in the subtask into 3 different terms as shown here. The first term can be borrowed from the base task, and the other terms contain one sparse matrix, which can lead to computation reduction. In this way, we are sharing computation across task domain, which is called task activation sharing. Third, to reduce the computation across time, we apply similar methods and use a sparse delta temporal activation matrix to reform these matrix multiplication. This can also lead to computation reduction because of the temporal activation sharing. Here, we compare our performance using single input image with state-of-the-art at NYU and Pascal datasets. Here you can see our method greatly outperforms the state-of-the-art in both datasets. We also compare our method with the state-of-the-art in terms of memory and flops for the video inputs. Our method is able to perform better in all tasks while requiring less parameters and computations. So in summary, we propose a novel computation and parameter sharing scheme for multiple visual tasks. Our method reuses the weights and activation of the base task for the subtask. Also, our evaluation results confirms that our method can have a better performance with fewer parameters and flops than the state-of-the-art. Thank you for listening.